Yeah, I want to begin by doing a sample problem. I've asked you to watch some of the videos, right? But I'm hoping they made sense. If they didn't, they surely should after the problem I'm going to do today. As you can imagine, simple vector addition problems I may not necessarily do in class. That's sort of the freshman physics effort. I'll do where we have to integrate and literally bring calculus into it. So what I want to do today is problem 2.7. The figure for 2.7 in your textbook is on page 66. So let me first describe the problem, draw the diagram. So you have a sphere, by that I mean a ball of radius, let me do it this way, radius uppercase R. And it says, and it has a surface charge density of sigma. The sigma itself is a constant, uniform charge distribution. And it says find the electric field everywhere. If you recall, so this is an area integral, and one of the things I wish to clarify is, well, it's 4 pi epsilon naught integral of what is it? Sigma r hat over r squared d a prime. Correct? Q has been replaced by sigma dA prime, and we want to know exactly what that means, prime, and so on and so forth. And this is the first time we'll actually do a physics problem where there's a distinction between prime and unprimed coordinate. And so they want us to compute the electric field everywhere. I will use two symbols. One is sigma and the other is total charge, but they are related. So it's total charge over the area. That is what sigma is. Find the electric field everywhere. So from spherical symmetry, you know the electric field is only dependent in magnitude on the radial distance from the origin, because this point is no different from this point. It's just that here it might point that way, and here it might point this way. Yeah? So what we will do is we'll pick one of the easiest points we can. Yeah? Along the z-axis. Now, in the entire sphere of that value of z, this will be the electric field. And we'll also calculate the direction, and so on and so forth. Okay, so if I look at this small chunk, it's a positive charge. Which way will the electric field point? Radially outward, right? So correct? And then, but the point, this is where I need, let me do it this way. I'm just trying not to clutter up the diagram. For every patch here, there is a patch here. And there is an equal in magnitude, but electric field, but that's pointing in. Perhaps it's a little more steeper than that. Yeah? So the electric field at this point, Z, that's the Z-axis. At this point, Z, is going to be, it depends, of course, on the height z, if you will, but which is the only direction it can point in? Upward, because this side cancels off that side. So all of a sudden, I don't need to do this integral. Because if I do this integral, of course, I'll have an upward component and a whole xy plane component that will cancel out when we do the integral. Why do something if you know it's going to cancel out in the first place? Yeah? So what I'm going to do is, what's the definition of EZ? Where EZ, I should really say Z component is equal to nothing more than E of Z dot K hat. That's what the Z component is. So, now I know the direction. It's going to be K hat. Now, what is the actual magnitude? Well, I take this and dot it with K hat. I can even bring the sigma outside at this point. I'm going to use the spherical coordinate system. So I'll make that very clear. So I'm going to use r squared sine theta prime d theta prime d phi prime. So here's the thing. I mean, I might even want to call it r prime squared, but it's a fixed constant. It doesn't really matter. R squared sine theta d phi is the area integral. But this is where the source is. So as I integrate over the sources, all the variables I use will be prime. Where am I evaluating the field? At this point z. I do not use prime. So to compute the electric field at one point, at an unprimed point, you have to integrate over all the prime surfaces. To evaluate the electric field at an unprimed, at a fixed one single unprimed coordinate, that's where you're evaluating the field, you have to integrate over all the primed regions. Only prime quantities are being integrated. And then you're left with an unprimed variable. That's where you're evaluating the field. So now it just matters for us two things. If there's a complexity, to write this down and then to integrate. Yes?
So what if the charge is inside it?
Well, then we'll have to do 0 to r. Then it will be a solid integral, and this won't be an uppercase r, it'll be a variable r prime. Yeah, good. So that's a good question. Don't erase anything, I'll put it back into this. What I mean by that is if you had to do that, I would do r prime squared dr prime and integrate that part too. But what we have is shell. It's a ball of radius r. Okay, so let me set up notation. So this patch, this is of course length r. Yeah, this coordinate is theta. Therefore, this side is r cosine theta, and this is r sine theta. From here to here, is z minus r cosine theta. correct? And this guy, this length here is that. So in particular, this one, well, it's just Pythagorean theorem. It is going to be r squared sine theta prime, huh? Theta prime. R squared sine squared theta prime plus z minus r cosine theta prime squared. Let's simplify that. I would get square root of r squared and sine squared and cosine squared would give me r squared, plus I'd get a z squared over here. Then I get a minus 2z r cosine theta prime. Yeah? Look and see why things are primed and why things are not primed. Okay, now I need this guy. This is k hat, this is r hat, and if I call this angle, say chi, r hat dot k hat is cosine of chi. Chi is just a temporary definition. I'll get rid of it right away. So if this is chi, this is chi. Tell me what cosine of chi is. Z minus r cosine theta prime. Almost. Cosine of chi, what is cosine? Adjacent over, huh? What is cosine? Correct, say it with confidence. Adjacent over hypotenuse. Yeah. So what's the hypotenuse?
Wait, which right? Script R.
Yeah, this guy. This is chi. Well, this is chi. So that r hat dot k hat, I write it as cosine chi. Why is that? R hat dot k hat is magnitude of r hat, which is 1, times the magnitude of k hat, which is 1, times the cosine of the angle between them. So I'm calling that angle chi. So if this is chi, then this is chi. Opposite angles are equal. And then when I look at chi, cosine is this over that. And so, easy, z component of E, which is also only a function of E, is going to be sigma, which I want to write it as, what is sigma? Q over 4 pi r squared, and 1 over 4 pi epsilon naught z minus r cosine theta prime divided by r squared plus z squared minus 2r z cosine theta prime d theta prime. I'm going to do the d phi integral, d theta prime. I'm I'm going to do the phi integral because phi doesn't show up at all. So I simply get a 2 pi. And this is 0 to pi. Yeah? At this point, we're almost done with physics, but we'll see we quite have it. But now it falls on us to integrate. Something like this, an integral like this, I don't expect you to just do it in class. There are always tricks to integrals. So something like this will be a take-home integral. Or I might make sure that I give you a relevant set of integration tables. Okay? You have to just stare, look at it for a while until you can actually integrate. So let me simplify this. And it will help me simplify. This and this becomes a 2. So I would get EZ is equal to Q over 8 pi epsilon naught. Oops, that's not true. Good.
You have that square term and then
You have a square term?
squared the root and then added that on.
Yep. One of the reasons I'm doing this problem is because I want to remind you of some cool techniques while you integrate.
So what happens in R squared?
Thank you.
So, with that r to the 3 over 2,
Yeah.
we use that r that we just found out from
Right.
earlier, right?
Yeah.
When you square it, wouldn't it be just that?
Yeah, but look at this. There's this plus times that. So I have r squared times r. And that means r cubed. R cubed. But r is this. This to the 1/2. 1/2 cubed is 3/2.
Where did that extra r come
From
from? That dot?
right here, from where I erased.
Yeah.
E has the
Oh, there's, oh yeah, I see, I
Yeah,
see.
yeah,
That's
yeah,
right,
yeah.
there's a small r.
Yeah, you have to keep track of it. So, what is this quantity? I bring it to minus. I have a minus 1/2 r squared plus z squared minus 2r z cosine theta prime to the 3/2 times the inside derivative 2 times z minus r cosine theta prime. Yeah? It seems like just something we can do. So, look at how it sort of turns out to be very handy because this is precisely what you have there. And so, easy equals Q over 8 pi epsilon naught r squared. I'm going to do a minus d dz. I pulled it out of the integral, and then I have 1 over square root of z squared plus r squared minus 2r z cosine theta prime d theta prime. I need a minus because of this minus to get rid of that minus. That minus is not there.
Why were we able to take the partials out of the middle?
Actually, when you do, it becomes a total derivative. What did I say? Yeah, r squared plus z squared minus 2r z cosine theta prime. Are we integrating with respect to z? It's a constant. So you can take the partial out. And I did that mostly for this reason. When you take it out, I mean, I can write it as d dz, but when I take it out, theta has already been integrated out. There's no more theta. So, in fact, I can replace it by, there's only z. So I can replace it by a total regular derivative. There's no more theta. Once you integrate theta, it's not a variable. Ooh. We forgot that there was a sine theta prime. Yeah. Well, good. Because the derivative of cosine, I think, is sine, right? Something like that comes in handy. That came from the integration measure.
Well, there's also an R squared. There's an R squared with the sine.
There's an r squared as well.
Yeah, capital R squared. That just cancels over there. What is-
Good. How did this r squared come? Oh, that's from the sigma. Yeah. Good catch. Now, what's the substitution? This is begging for a substitution. What's the derivative of cosine theta? Isn't it negative sine theta? Theta prime. And that is beautiful because I love it where I can easily erase and you guys have to rewrite it in the next line. So what do? I multiply by yeah? And then I have minus q over 8 pi epsilon naught 1 over 2r d dz 1 over z integral of what? du over square root of u. We'll integrate it, write it back in terms of sine and cosine, and put in the limits. What's the integral of this guy?
1 over 2 over
So please make sure that I'm not dropping. If you think like I'm dropping an r squared and sine theta, we'll eventually catch it when we do the integral. But what is it?
1 over 2 square root of x. I mean, u.
Square root of u over 2?
I mean, and then you can just write it out.
So are you telling me it is
1 over
is there a minus?
That could be 1, 2.
Or is it 2? U to the minus 1/2 becomes plus 1/2 divided by 1/2.
And then you get 2.
2 upstairs.
Yeah.
Yeah.
I don't know, maybe that's it.
Please check, because otherwise we'll have to track the mistake down. I think I have a semi-cleaned up version here. Semi is good enough, right? Yeah. So I think we're, and then of course, I need to set the limits now from 0 to pi. I love to do examples, but the problem is we cover, we're only able to cover one example a day. All right, so I'm going to, again, like I said, everything I do will have a purpose. So 2's will cancel, minus q over 8 pi epsilon naught r d z 1 over z. Cosine of pi is what? Sorry? -1. So this becomes a r squared plus z squared minus 2rz. So that is z plus r whole squared. Yeah?
Isn't that a 2 over z, or you cancel it?
2z.
Oh, you did.
Yeah? So when I take the square root, what do I get? I'm sorry? It would almost be r plus z. And this is a lesson we have to remind ourselves all the time. What is that? No, it's not. Plus or minus. Huh? It is 3. Yeah, but this notation we strictly mean, this will never be a negative number. So no matter how you evaluate it, at the end, it has to be a positive number. Yeah? So it is z plus r, but it's the absolute value. Oh, let me ask you this now. You might,
That's got 2 solutions. That's -3 and plus or minus.
yeah, the solution to this is plus or minus 3. But what is this? Only 3. If one is plus r, the other one is minus r. So the math is over. Back to physics. Yeah? I don't know how to take absolute value just everywhere, so I have to break it into 2 regions. So region 1, when z is greater than r. So then the electric field is equal to minus q over 8 pi epsilon naught r d z Z. Z is greater than R, so as far as I can tell, that's a positive number. Z is greater than R. So Z minus R is a positive number. Okay, so then that's minus Q over 8 pi epsilon naught R ddz, 1 over Z. What happens when you simplify? You would get 2R. Derivative of 1 over Z is what? Negative 1 over Z squared. So I would get Q over 4 pi epsilon naught 1 over Z squared. Yeah? Or the familiar KQ over Z squared after all this trouble. Yeah? So the point is, you cannot distinguish from a field point of view a sphere from a point charge. Yeah? If you have a multimeter and you see a charged death star, you don't know if it's a death star or a death point. It looks exactly the same way. Yeah? Valuable lessons in the life of Luke Skywalker. There's no way to distinguish perfect spherical symmetry. These things are very profound statements in physics you're encountering for the first time, so you're perhaps going, yeah, well, that sounds good. There's an equivalent version for this in general relativity. If you have a star that has collapsed into a black hole, if you have a spherically symmetric black hole, there's only one solution. It's called the Schwarzschild black hole. There are no other solutions. In fact, gravity cannot radiate in a spherically symmetric star cannot radiate gravitational energy. There's only one solution. It's this kind of a solution. In general relativity, it takes on a different form. Yeah, but there's only one and one type. There's no time dependence. So spherical symmetry is a very powerful thing. It's very special in the universe. You make it axially symmetric, we'll see, and gosh, we'll have all types of solutions. Many, we'll construct many. The moment it is a football, you've distorted it from spherical symmetry. Now you have many types of solutions. Unless it's a black hole, which Hawking showed that there's only one type of black hole that can spin. It has a little bit of a bulge. It loses its spherical symmetry. If you have axially symmetric, there's only one type of black hole. If it's a black hole. But if it's a star, well, you can have many solutions. Yeah. All right. Now let's find Z is less than R. Of course, I mean, and Z greater than 0. We're just going over here. Because if you flip, it's the same electric field, just points in the other way. We don't care about that. So in that case, please make sure I'm copying down Z plus R, Z plus R, minus Z is less than R. So what's the absolute value? R minus Z. What is that? 2z. R minus R, then minus minus z becomes a 2z. And guess what happens? The z's cancel. What's the derivative of 2? There is no electric field inside a ball.
The ball, you mean like there's stuff inside?
There's no stuff inside, it's vacuum inside.
So it's like
A ball.
the casing, like the
Shell.
Shell.
Yeah, so we have a shell of charges. What you're saying is we're inside the shell.
Yeah, nowhere inside the shell there is an electric field. A spherical shell completely shields it. Amazing. Let me go back to my Death Star. If it were in fact a death shell, people would be floating inside it. There would be no gravitational field. Why? Because Coulomb's law is K Q1 Q2 over R squared. Newton's law of gravitation is G M1 M2 over R squared. It's the same thing, just the constants are different.